In the previous lecture, we gave a computationally amenable form for describing an extreme point of a polyhedron, and this is how we did it. So suppose we have P, which is defined by a certain bunch of linear inequalities. So x in Rn such that Ax less than B. So in that case, any point V in P is an extreme point of P if and only if n of these, so x is in Rn, this polyhedron is in Rn, so V in P is an extreme point of P if and only if there are n linearly independent constants among these constants. There are n, so n is this dimension n. There are n linearly independent constants amongst Ax less than equal to B that satisfy equality at V. So we had a geometric description of what an extreme points of a polyhedron looks like, and here this is a computational way of thinking about extreme points. Here we have an array of numbers A and an array of numbers B. Based on that, so this linear independence has nothing to do with B at all, so it's something to keep in mind. So when we say there are n linearly independent constants, we are just focusing on the rows of A. So this is nothing but each of these rows of A times x is less than equal to a number which is essentially an element of this column vector B. So each of those row vectors of A, so we want to find n linearly independent row vectors in A. So that's what it means. And for each of them you have that, let's say we are talking about the first row, then we have A11 all the way up to A1n acting on this column vector x is in fact equal to B1. So in that case we say that this, or rather I should say V here. So this point V is said to be satisfying equality for this constant, or it's said to be tight at V. So this constant is said to be tight at V. Alright, so just to clarify, this linear independence has nothing to do with B and this inequality whatsoever. It has to do with linear independence of rows of A. So geometrically, how do we think of this idea? It's like saying if I have two half spaces, then their intersection will be one dimension lower. Or rather, if I have two hyperplanes, their intersection will be one dimension lower, and an extreme point will only lie on the surface of the convex body. So if you have something like satisfying, like V satisfying two of these inequality constants, so generically if in R3 you have two hyperplanes, the intersection will be a line. Then if you bring in another hyperplane, generically it will intersect this line at a point. So eventually if you have three generic hyperplanes, so to say, so generic here will be captured by the idea of linear independence. So that's what it's saying, that no two of them kind of determine the third one in this case. So in that case, as you take the intersections, the dimension goes lower because of the linear independence. So in order to get to 0 dimensions, so if you started with one hyperplane, that's n minus 1 dimensions, you take another hyperplane, then their intersection goes down, like the dimension of their intersection goes down by 1. So you get something which is n minus 2 dimensional. And if you want to reach 0 dimensionality, so you have to take n of them. So at each time you do an intersection, you will go one dimension lower. Eventually you'll reach this extreme point. So that's what geometrically this means. So we had proved this result. And the last thing we discussed was about boundedness or unboundedness of an LP. So generally we have been talking about LP in standard form. So we have been denoting it by LPS. So you have this cost vector C, and you have these vectors X determined by a feasible set, which was a polyhedron. So Cx, we want to minimize this objective function. On F, which is a polyhedron in Rn. So X is a vector in Rn, and C is a fixed vector in Rn. So keeping that in mind, so there are many questions that we can ask ourselves. Like, this is a general question that has been posed. So one thing is this function even bounded on that set? So we had defined the last definition we had given in the previous lecture was an LP in standard form or in general. It doesn't have to be in standard form. So if we are talking about a minimization problem, then we will say it is unbounded if there is no minima. So you can always, like, given any number, you can always find some vector x in the feasible set such that c dot x is less than equal to that number. So you can always do better. So in that case, the LP is unbounded. So there is not much to do. You cannot really find an optimal value there. And similarly for maximization problems. All right. So before we move on, I want to phrase all of this discussion as a series of questions. So this will, like, kind of help us keep like focused on to what our end goal is. So let me summarize that first. So we want to, okay, I'll repeat this again. So we want to minimize c dot x over f using a computational algorithm. So that has always been our end goal. And the reason we want a computational algorithm is because we have realized that there is no closed form solution for LP in standard form. So we want to see if we can, like, make a computer do the hard work. All right. So before we can do that, the first question comes to our mind is, we want to make a computer understand the problem first before even it can solve it. So the first question is, what data structure can store a complete description of f? What data structure can store a complete description of f? And for this we have a very good answer. In fact, we did all those representation theorems. But in any case, f is a polyhedron, and the way it's defined is by all these inequalities. So all you have to do is specify two arrays. So answer, so specify two arrays. So that's how you, like, tell a computer what f is. So A, it will be an m by n array where n is the dimension of the of whatever space your vector x lies in, and m is the number of inequality constants that you have. So A is an array, and B is also an array. So array of size m by n, and here you can say it's an array of size m by 1. Okay, so for this we have a good answer, and we did some hard work to gain this. And if we, and this is not the only data structure for f. We saw that f in fact has finitely many extreme points, and we proved it in two different ways. In the sense, the first way we proved it in a more geometrical fashion, but for the second thing, for LP in standard form, we were able to show that basic feasible solutions are vertices, and there are finitely many of them. So we have taken a good look at this. So there is another representation of f, and that is using a certain, like, number of vectors. So that is the extreme point representation or extremal representation. But in any case, this suffices. In fact, for f, that is the defining property. It is governed by all these inequality constants. So we know how to make a computer understand what f is. Now the second question comes to mind is, how do we decide whether f is empty or non-empty? So how does, before we can even solve LP, this is the kind of question we want to answer. Is this even like is it a vacuous problem that we're trying to solve? So how does a computer decide whether f is empty or not? So some sort of oracle program, you feed it A and B. So that is the computer, like the data structure that we're using. So A and B, feeding A and B to the computer just means telling it what are the, like, constant determining f. Now the computer has to, like, tell you an answer, like, is this an empty set or not? So it's like an oracle program giving a yes or no answer kind of thing. And for this, I had mentioned that we will need some concepts from duality, theorems of alternatives, so to say. So we'll not be answering this question right now, because typically whenever you are designing an LP, you always have a single solution in that set, in the sense of, in the very, in the first few lectures we had discussed an example about, you have a certain plot of land and you have certain fertilizer and pesticide. Like, you want to figure out how much land to assigned to wheat and how much land to assign to maize, so that it's very clear that it's not an empty problem, because what I can do is choose to not do anything at all. No wheat, no maize, nothing. And in that case, my revenue is going to be 0. So it is that is a feasible thing to do, like not do anything at all. So there, whether this f is empty or not, you can just look at a quick example and figure that out. But often in many, like say linear programming problems, let's say arising from mathematics, or where you don't have such a very good handle over things like feasibility, then you want this sort of oracle program. But for many practical problems, you already have one solution. You may not know it's the optimal solution, but it is a solution that works for you, and you want to do better than that. So that's why this problem, even though we have not answered it, but that's not really that big of an issue in practice. Okay. What's the third question? So we're going to phrase it as 4 questions. The whole of linear programming that we have been studying, we are going to phrase it as 4 questions. And by the way, so I when I phrase these questions, these are meant to be understood in the sense that we want to empathize with a computer. We want to make a computer understand these questions. We do understand what we have to do, but we want to think in a very systematic manner. We want to know whether each and every single step can be understood by a computer, and it can give something, some meaningful answer. All right, so let's say the computer has figured out. If it says f is empty, then there's nothing to do, right? The LP is like ill-posed, or whatever phrase you want to use. It's not very useful. So if the oracle program has figured out if it is non-empty, so then let's move on. If f is non-empty, what is the next issue that can arise? So how does a computer decide whether the LP is bounded or not? Whether the LP is bounded or not. We need this, because if it is not bounded, then again we don't really have an optimal solution. So in that case, either you realize that the question is ill-posed. So I mean, in practice that's like very unlikely to happen, but so it gives you a hint that you're missing something in your model. Or if it arises from like a more mathematical like standpoint, then yeah, I mean, then that's already an answer of some sorts. Okay. And the first question is the one that is the most relevant. That's why we're keeping it to the last, to the very end. So if f is non-empty and the LP is bounded, meaning there is a definite solution, there is a definite answer to the question of what is an optimal solution, and the LP is bounded, then so how does a computer find an optimal solution? So this, again, as you can guess, is the heart of the simplex algorithm. So we're building up towards that. And as I said, like question 2, we will figure out some ways to determine this, but right now, like as I said, like typically you will have some feasible solution, so you know that it is non-empty. So the whole like crux of this lecture is question number 3. So this is the question which we will answer in today's lecture. I had already phrased this as a question, but I want to phrase it as a bunch of questions. I had phrased that theorem in the previous lecture towards the very end, but here I want to phrase the whole of the a major chunk of this course as 4 questions that we're trying to answer, and today's lecture will finally answer question number 3. Like how can we algorithmically decide whether the LP is bounded or not? And we will actually say something more than that, but this will be, say, a corollary of the result we'll be proving. Let me state it. So theorem in LPS, meaning LP in standard form, suppose that P is a feasible vector, a feasible point. Suppose that P is in the feasible set. So feasible set is non-empty. So look back at the question. Question number 3 is if F is non-empty, so such a P does exist. then either the LPS is unbounded or there is a vertex V of F which actually does better than P. So there is a vertex V of F satisfying C dot V, or C, which is nothing but C transpose V, is less than equal to C dot P, which is, this is the objective function. So what this is saying is, if you give me any point in the feasible set, then either this LPS is unbounded or I can find something better than that, and that in fact has this property, it's a vertex. And we have seen in LPS that polyhedron has finitely many vertices. So in the previous lecture we had actually discussed a corollary of this. We had said that either the LPS is unbounded or we have like finitely many vertices to choose from. So all you have to do is figure out a way to navigate these vertices, and that is exactly what the simplex algorithm will do. It will tell you how to like you start with some vertex and how to move around in an efficient manner and then find the best possible vertex. So the answer lies in the vertices. The rest you don't even need to talk about them. All right. So the main matter of this lecture will be about proving this theorem. The corollary we have already seen, and it will in fact result in an algorithm where one of the conclusions of that algorithm, you start with a point P. So it will be able to conclude that the LPS is unbounded, like in a systematic manner, step-by-step manner, or if it is not unbounded, then it will in fact return a vertex which is better than P. So this is not just a very mathematical existence kind of proof, it is a very explicit algorithm. So let's go ahead. And the thing to note is it is LP in standard form, so we have AX equals B. And so the feasible set is essentially determined by this, and X is bigger than or equal to 0. So this is what F looks like. All those X in Rn such that Ax equals B, and all the components, individual components of this vector X, they are all bigger than or equal to 0. So since P is in F, so clearly AP is equal to B, and the notation we have been using, Pi is bigger than or equal to 0 for all I in 1 through n. So Pi is the ith coordinate. This is just rewriting this fact that P is in F. Okay. So now the very strategy of the proof will go as follows. So you have Ax equals B, these equality constants, and then you put the sign constants. So you have all this being bigger than or equal to the vector 0. So essentially this will be like an identity matrix. This will refer to x1 being bigger than or equal to 0. This will be like x2 bigger than or equal to 0, and so on. So this will be an n by n identity matrix, and this is m by n, right? And m is less than or equal to n because we have been assuming A is a full rank. M by n matrix, and m is less than or equal to n. So overall, if I do this, so this is I n and A, so this matrix has dimension m plus n times n, because m rows here and n rows here, and columns anyway, there are only n columns. So we have arranged all the sign constants first and the equality constants at the bottom. So the strategy of the, so this is just the notation. I'm setting up the notation. Now what we will do is take all sets of linearly independent constraints that contain the constraints Ax equals B and all of which are tight at P. Okay. So anyway, these constants are tight at P simply because they satisfy equality. So what are we doing here? So we are taking all sets of linearly independent constants. So remember, I said when we are talking about linear independence of constants, then we don't really care about this B. What we are caring about is row vectors of A. So anyway, A is a full rank. So all the row vectors of A are linearly independent. So you have M linearly independent like row vectors here. Now what you want to figure out is add the max, like you want to take like all these additional sign constants here which satisfy equality at this chosen point P. This is the point P you started with. And what does this mean? All of which are tight at P. That just means that you're choosing those constants where Pj is equal to 0. You're choosing those J's where Pj is 0. That's what tightness means here. It satisfies like in this inequality constant, you're satisfying equality. So yeah, so we take all those sets and then we choose the largest possible. So choose a largest one, S in 1, 2 all the way up to m plus n. So here we have to be a bit careful because we're setting up notation. If you are lost here, then it's hard to come back. So I'll restate this. I have m plus n rows and I want to include all the rows of A. They're linearly independent. So essentially I want to form a basis of Rn by adding certain rows here, but those rows have to satisfy this tightness condition at P. So there Pj has to be 0. If it is not, then it is quite possible that none of the Pj's are 0. Then I don't get to choose any like any of these indices at all. So choose the largest one, S. So that S could just be the set n plus 1. Remember, we have put the sign constant first. So n plus 1 through m plus n are always going to be there. n plus 1 through n plus m. So these are m many rows. So these things will be always there. But you want to choose from 1 to the sign constant 1 to all the way up to n, which is like the largest extension you can do of these row vectors of A and staying linearly independent. So choose largest such one and let R equals cardinality of S. So what is really R? R is actually rank of this matrix INA. So that is precisely rank. You have all the linearly independent vectors here. How many of these vectors can I add? Actually I take that back, sorry. So it's not really the rank of this because we have this additional condition. If I had stopped here, then it would be rank of that. But since I care about not only adding those rows which are linearly independent of A and amongst each other, but also they satisfy these conditions Pj equals 0. So keep that in mind. So R is cardinality of that such a set, and then you are denoting I by S intersection 1, 2 all the way up to n. So these are just the sign constants in S. So repeating myself again, S will contain everything from n plus 1 to n plus n. That's because it contains all the row vectors of A. You are adding certain rows from the sign constants where equality is achieved, and amongst them you are choosing the largest possible set, and you are denoting I by whatever additional things you have to add to the rows of A. Okay, so I is consists of the R minus M sign constants in S. So this is the first step. You choose such a S. There might be more than one. You choose one of them. That is good enough for us. So in step 2, what do we do? If R is equal to n, so what happens if R is equal to n? Of course, R cannot be bigger than equal to n because R is going to be less than equal to rank of this big matrix consisting of n by n identity padded with this I. So if R equals n, that means you have n linearly independent constants which are tight at P. What does that tell us about P? From a previous lemma, P is a vertex of F. If R equals n, P is a vertex of F. We are done, because what was the assertion in the theorem? That we can find a vertex where the cost function or the objective function is less than or equal to the cost function at P, and P in this if R is equal to N, P is already a vertex, and we choose V equals P, so we'll be done. If that is not the case, then R has to be less than equal to N or strictly less than N. So the third case, so if R is less than N, in fact this is the meat of the proof, we will show that either you have that this objective function C dot X, and here of course for X in the feasible set, can be made arbitrarily small, and as you can immediately guess, if this option is the one that holds, then the LP in standard form is unbounded, can be made arbitrarily small, or the second option is there exists something better. So there exists another vector in the feasible set such that first of all it has it is a smaller cost, it is of smaller cost, so this holds. And remember, if P star were a vertex, then we are done, but I'm not claiming that the other option is that P star is a vertex, but it is something better than P. It is actually one dimension lower in terms of satisfying like all these hyperplane equalities, so such that it has a better like it has a better cost than P star, and for which there is a larger set of linearly independent constraints. There is a larger set of linearly independent constraints tight at P. Tight at P star, sorry. So what happens now? Now if you think of, so see, so we started with the point P, this number R is in fact associated with P. In fact, I should probably write it as RP. Now what I'm going to do is, if this claim is true, I mean, like I said, this is proving this number 3 is the meat of this proof. So assuming this is true, so for this new P star there is also another R, but what this condition is saying, that there is a larger set of linearly independent constants tight at P star, it's just saying that my RP star is strictly bigger than RP. So then if that RP star is equal to N, we go back to step number 2. Then P star is a vertex of F. If not, we come back to step 3 and keep doing this. But we do know that since the rank of this matrix INA is less than equal to N, this process is a finite process. It has to terminate at some point. So how do we finish the proof? Like once 3 has been proved, iterating the process at most n minus m times. And what does this number n minus m come from? That's because we know that R has to be, it's not just less than n, but it is also bigger than equal to m, because all those row vectors of A which are linearly independent by our definition of S, they're always in S. Okay, so iterating this process at most n minus m times, either this condition holds, and once this condition holds, you just terminate, because you know that this LPS is unbounded. But if the other condition holds, you keep repeating this whole step for this new point P star, and this condition, this first condition, might hold in one of those cases. I'm not saying that every step like it will hold. Whenever it starts, like whenever that assertion is true, then you just quit, like in this algorithmic process. In fact, at the end I'll give you a pseudocode for this, so no worries, we'll actually write it as a step-by-step kind of algorithm, but for now we're looking at the mathematical aspects of this result. Alright, so iterating the process at most n minus m times, we either find a proof that the cost is unbounded, or we reach a or we reach a vertex V such that C dot V is less than equal to C dot P. I mean, you'll have P, then P star, then P star star, whatever, and at each level this cost function is reducing. So eventually when you end up with a vertex, that cost function has to be less than equal to the cost function of the original point. Okay, so a quick observation here. Now recall, since S was the largest set of indices, since S was the largest set of indices, such that the corresponding constraints are tights on S. So indices, you can just think of, we have named the rows, right? So I and A. So overall we had this vector 0 vector padded with this vector B. We had equality here. So indexes, you have named it 1 to all the way up to m plus n. So since S was the largest set of indices from in 1 to m plus n, such that the corresponding constraints are tight at S, then if Pj equals 0 for j not in S, what is that saying? That Pj must be strictly bigger than 0, because these sign constraints are just saying it's bigger than or equal to 0. So if j is not in S, okay, I think if Pj is 0, that is if Pj is 0 for j not in S, that is if xj bigger than or equal to 0 is a sign constant which is tight at P, then it must be linearly dependent on the tight constants S. Yeah, on the tight constants corresponding to S. So again, to repeat myself, so we have chosen some indices containing all the things from n plus 1 to n plus n, containing all the row vectors of A. So we have equality there, and that is a maximal such set in here. Now if outside of S I have a point where Pj is 0, that means Pj has a has equality here, or it is tight there, or the vector P is tight at this constant j, then it must be linearly dependent on the rest of the tight constants, because if it were linearly independent, then S would not be the largest, you would have to add that index. So this is just an observation, just unraveling all the definitions. All right. So now what we like, the way we want to strategize, I think geometrically is viewed best. So 3 dimensions, we have some degrees of freedom. So let's say generically you started with some point P, it was in the interior somewhere here. Okay, let me choose this as a vertex, some point here which was in the interior. So this is the point. Now what you want to do is pick a direction where the cost function decreases. So you want to pick a direction and you want to just move along that direction. And what happens when you move along the direction is you hit a face, and that face essentially, I mean, you could hit an edge, in fact you could hit a vertex, but generically what would happen is you'll hit a face. So here the cost has decreased, but what does the face of this tetrahedron look like? It looks like a triangle. So now within the triangle you want to find a direction where the cost is decreasing. So you go around and then you hit an edge. Now you look at the edge and you go along a direction, then you hit a vertex. So you just want to find a direction where the cost will decrease, and that has to kind of, I mean, we'll show that, but intuitively you can think that that direction has to exist, because if this is in the hyperplane which is perpendicular to C, because that's how so C dot x equals alpha, so this is the cost function equals alpha determines the hyperplane which is orthogonal to C. So then there has to be some direction where this value, this projection value, is decreasing. In fact, that is the offset. This alpha is the offset, right, from the origin. So there has to be one direction. So if you're in the interior, you just move along that direction and stay within your feasible set. So that's the general idea. But that's because if I put in a few equations, it's going to be very confusing and you'd feel like you have to memorize all this. But geometrically, this is what's going on. I'm going to define this set. Let f star be all those vectors in Rn such that xj equals 0 for all j in the index I. Recall, what is I? I was nothing but S intersection 1 through n. So S was the largest set where you had all the constants being tight at P. So although we are writing S, you should always remember it is in fact SP. It depends on P. So all those constants that were tight at P, and introduce maximal such containing all the row vectors of A, or corresponding indices. So we want to look at all those vectors x such that x in Rn such that xj is 0 for all j in that for those indices, and Ax is equal to the 0 vector. Okay, so why do we want to look at this set? Now if I replace this 0 by b, so what happens then? This is precisely saying, first of all, Ax is equal to b and all these xj's are 0. So f star will contain p, right? Because pj is 0 for all j in I, because the equality constants are tight, or rather the sign constants are tight for all those indices j. So remember, the vector p is in f star minus b. Or rather plus b. Yeah, f star plus b. So here it is just figuring out all those directions where you can perturb p. So just look at these pictures that I drew. We want to perturb b in a certain direction. We want to move along so that we go to some place where the dimension is lower, and also we're reducing the cost function. So the purpose of defining this f star is it's not talking about absolutely about a vector. It's talking about the direction of perturbation within that polyhedron, the feasible set F. So that is a point that one has to keep in mind, the geometric picture. So, and the reason is because if I do something like this, Ax plus like lambda w, where w belongs to f star, what happens? Because aw is 0 from this equation, then Ax plus lambda w is nothing but Ax is equal to b if x is in f. Then the question becomes whether x plus lambda w is in the feasible region or not. And when I'm writing x plus lambda w, I'm talking about perturbations of x in the direction of w. So in fact, f star is telling me all those directions in which I can perturb my p, and yeah, and with all these constants xj set to 0. So and why is this valuable? That just tells me I can perturb it both ways. Because if I start with p and pj is 0 and I have some direction where xj is strictly bigger than 0, if I go in the other direction, then pj, the value is going to like decline. But if xj is 0, whenever I take lambda w and minus lambda w, doesn't matter, both of them lambda of wj is 0. So I'm still within that feasible set going in either of these directions. Yeah, because if I'm already on a face, that means I cannot move in this direction, then I don't really want to go inside. So that's the whole point. Okay. So now what is the dimension of f star? So dimension of f star is n minus r by rank nullity theorem. So why so? So where did the rank nullity theorem come from? So if you look at all these together, so this is not just one equation. I can just say that so xj equals 0, I can pad it with this, right? I'll take those corresponding row vectors and pad it with a. Essentially I'm trying to solve that times x equals 0. So how many entries does it have? It have m things here. So total number of elements of S is equal to R. That is how we had defined it. So we have a R by N matrix. So this is R, this is N. So we have an R by N matrix X equals 0. We're trying to solve this. So clearly, I mean, F star is the nullity of this matrix, and we know that this has rank R. These are all linearly independent columns. So rank R, rank is equal to R. So nullity must be N minus R, right? So dimension of F star equals N minus R by rank nullity theorem, and this is strictly bigger than 0. You know, R is strictly less than N. Okay. Just wait a second. Yeah, right. Yeah, so rank is R. So dimension of F star is N minus R. So if, I should just write, if R is strictly less than N. So go back to the strategy that we had like mentioned. So if R is equal to N, P is already a vertex, nothing to do there. Like, and that was from a previous lemma where we described a vertex of F as being determined by N linearly independent like constants which were tight at P. So that's why we're in at level 3. We have assumed R is strictly less than N. So if R is less than N, there is a vector, non-zero vector, there is a non-zero vector W in F star. That's because the nullity is like not 0, so the kernel is non-trivial. So you just choose something which is non-trivial in the kernel. And another thing we can do is assume C dot W is less than equal to 0. So what was W? Recall, W is our choice. We have chosen a vector, this W is in F star, satisfying this equation Ax equals 0 and Xj equals 0 for all those indices where Pj is 0. And you had this linear independence assumption also. Like you had this maximal set of linearly independent elements where, and they were all corresponding to P. So I want to always remind you that this set always depends on the point we have chosen, started with P. Okay, and why can we assume C dot W is less than equal to 0? Because if it is bigger than 0, then you can always change the direction. Change W to minus W. It will still satisfy all these conditions, Xj is 0 and X equals 0 and so on. I have not said that these points belong to the feasible set and so on. I have not made any such requirements of X. So that's why I can always negate W and ensure that the cost function is less than equal to 0. And I would like to remind you, this geometric picture is the reason why we have all these constraints. Xj is 0 is so that we can perturb in both directions. We want to perturb P along the direction of W and still stay within our feasible set. But if you don't have these type of constraints, there will be one direction where you can go and stay within the feasible set but not in the other direction. Then there is no use moving around in this direction. Okay, so in any case, we can always assume this. So by negating W if necessary. Okay, so now here's a claim. If Pj is 0, then Wj is also 0. And this is actually a very straightforward claim, but we want to observe a little bit more because it almost looks like this was the definition, but it's not, right? Here we had the definition of, so W is in F star. W is in F star, so that means Wj is 0 for all j in these indices. But I'm not saying S is the set of all j's such that Pj is 0. It is the set of all j's where Pj is 0, and it's a maximal set where those rows are also linearly independent when you pad in all the row vectors of A. For example, P could be the 0 vector. That means all these indices are tight. But then you cannot include all these indices because you have this m plus n by n matrix which can have maximum, it can have like rank n, and you already have to choose these m row vectors. Like that's how we have defined our S. So the maximum you can choose from all these sign constraints is you can choose n minus m, many of them. So here I'm asserting something more. I'm just saying that if pj is 0 from the remaining constraints outside of I or outside of S, then wj also satisfies that. Alright, quick proof of the claim. Let's say if pj is 0 and j is not in this indexing set I, because if j is already in the indexing set of I, j is in I, then wj is 0. That was how f star was defined. So we want to prove this in the rest of the cases. So j not in I. Okay, so anyway, let me state it. So wj is 0 for j in I by definition of f star. Right here. W is a vector in f star. So wj is 0 for j in I. So for j not in I, we want to show this. If pj is 0 and j is not in I, then the constraint xj bigger than equal to 0, which is tight at p, must be linearly dependent. That was the observation that we had made. So that is the observation is what we are using here. Because if it were not linearly dependent, then you can always add it to S and increase the size of this set S, and S was the maximal such possible such thing. So that's why this constraint must be linearly dependent. So this must be linearly dependent on the constraints in S. So in that case, naturally, so if you, let's say it was 0 0, like this was the corresponding sign constant, so this is like the jth column. So what I'm saying is this row vector is a linear combination of lambda 1 of all those row vectors, and so it's a linear combination of the corresponding j's in I, in fact S. So lambda I, let's say ai, where I belongs to S. These are the rows of INA, and each of them, the inner product at P is 0, and in fact at W is also 0. So AI dot W is 0 for I in S, right? That's how we define W, which means if I take a linear combination, so since this 0 0 1 0 0 whatever this is, it's a linear combination of the lambda i's. So this times W, which is Wj. So Wj is, let's call this Ej. So it's Ej inner product with W, and what is Ej? It's lambda I ai summation I belongs to j W, which is nothing but summation over I belongs to j of ai dot W. But these are the constant, like W is tight here at all of these places. So all of these are equal to 0. So what we conclude is Wj is 0. This is something very, very straightforward. Like I explicitly wrote it out, but you can immediately see there is a linear relation between these, and we know that for the remaining things, W, when these vectors act on W, we get 0, because that's the way we defined it. So of course, when this acts on this W, it also has to be 0. But as it turns out that when this vector right here, Ej, acts on W, it gives you the Wjth coordinate. So also for j not in I, we have proved this. So whenever Pj is 0, we have Wj is also 0. Okay. So for all lambda in R, remember not R plus, not R minus, but all positive real numbers, you have this as AW0, and the geometry picture is you started with P and you're perturbing it in a certain direction. And still here we have not made any assertions, but we want to find such W, and that is our goal, so that when we are moving along these directions we still stay within our feasible set. Okay, that will be what we do next, but yeah, right now, so if Pj is 0, what have we concluded? Then P plus lambda W of j is also 0. So why so? That's because Wj is 0. That's precisely the claim. If Pj is 0, then Wj is 0, period. Like no matter what index j you choose, it doesn't have to be from within S. So clearly, because of that, whenever Pj is 0, we have, whenever you're perturbing this, we always have this extra constraint that the jth coordinate is 0. Okay. Now for lambda in R, P plus lambda W clearly satisfies the equality constraints. Satisfies the equality constraints of LPS. This is what we just saw. Okay, now what we want to prove is the following. To prove one of the two following possibilities happens. So one of them is we may choose lambda arbitrarily large and still stay within F. Large in such a way that P plus lambda W is in F. And as you can imagine, if F were like some sort of compact set, this will never be the case, right? There will be, if you choose lambda too big in either direction, positive or negative direction, you will always exit this set. But of course, F need not be compact. So here, that's why we're exploring these two possibilities. We may choose lambda arbitrarily large in such a way that P plus lambda W is in F, and C P plus lambda W can be made arbitrarily small. So why is that? First of all, C dot P will be a fixed constant. Then you have lambda C dot W. If C dot W is strictly negative, then of course, if you choose lambda to be arbitrarily large, then the cost will like reduce as much as you want. And if C dot W is equal to 0, okay, so that's something we'll have to look into. Yeah, so here we're just outlining the whole thing. Or there is lambda in R. Think about, so yeah, let me just make a note. Think about C dot W equals 0. All right, otherwise you have lambda in R such that C P plus lambda W is less than equal to C P, and at least one more sign constraint. At least one more sign constraint is tight at P plus lambda W than at P. and that sign constant is linearly independent from the constants in S. So you can add that to S. You can make S a bigger set for P plus lambda W. This is your P star. And that sign constant is linearly independent from the constants in S. So for this new point, if I'm calling this, let's say P star, then the and you are able to add like one more index where the sign constant is tight, then this S will also be updated. That's why I had told you that S in fact depends on P. So here also, if you replace P with P plus lambda W, you'll have to think of the new S as the one which also contains this new index. All right. So we may choose, so let me revisit these two possibilities. We may choose lambda arbitrarily large so that this belongs to F and this can be made arbitrarily small. Yeah, this is a case which we'll also consider, so no worries. But yeah, otherwise there is a lambda such that you can in fact do a little bit better. So it's starting to tend towards a vertex. So this P plus lambda W, it satisfies sign constants and they are linearly independent, and it has in fact one more. It satisfies one more equality constraint than P. So it is kind of tending towards a vertex. If it satisfied n like linearly independent like equality constants, then it would be a vertex by one of our previous lemmas. That would be R equals n. That was the case too. All right. So now coming to the meat of the proof, let J be all those indices where Wj is less than 0. In fact, this is going to be an element of this minus I. So why so? Because we have checked that for all those things in I, what happens is Pj is 0, and whenever Pj is 0, Wj is 0. So if it is true that Wj is strictly less than 0, it cannot belong to I. So we're choosing this set of indices where Wj is strictly less than 0. And this could be an empty set. So we'll consider all those possibilities. So first of all, case 1. Okay, I think here this assertion was not necessary, because all I'm saying is we may choose lambda arbitrarily large so that this is in F and this can be made arbitrarily small. So both are part of the assertion. Otherwise, you can do like you can replace P with something which satisfies equality at one more sign constant. Okay. Anyway, so coming back to this, so case 1 is C dot W is strictly less than 0 and J is empty. That is, Wj is bigger than or equal to 0 for all j in 1 through m plus n. So it is never negative. So remember, by our choice of W, we had ensured that this is less than or equal to 0. Here I'm assuming it is strictly less than 0. So that is my case 1. So one thing to notice is, so P plus lambda W is in F, right? Because anyway P plus lambda W, like for all lambda bigger than or equal to 0. Yeah, so anyway for all lambda, P plus lambda W satisfied the equality constants. That's what we had observed here, right here. The only problem was, what about the sign constants? But now that we have assumed J is empty, that means Wj is bigger than or equal to 0, so they're all positive. So that means if I take lambda to be positive or non-negative, then P plus lambda W also satisfies all the sign constants. So this is going to be true. Now, what about this, the cost of P plus lambda W? So this is in fact C dot P plus lambda times C dot W, and this is going to be strictly less than 0. So why so? That's because this is c dot p is just a fixed constant, because p is what we chose in the very beginning. It's a point in the feasible set. C is fixed, p is fixed, so this is a fixed number. And here lambda, what we have noticed is that for all lambda bigger than or equal to 0, lambda, like p plus lambda w, is in the feasible set. And the c dot w is actually strictly negative number. So lambda times this is like, if you increase the value of lambda, this actually decreases, right? And it goes all the way up to minus infinity. So you can choose lambda big enough such that c dot p plus lambda w is strictly less than 0. At the same time, this is in f, belongs to f. So what you have been able to do is replace p with something, p plus lambda w, and whose value actually goes to minus infinity. So that actually takes care of this part. We can choose lambda arbitrarily large in such a way that this holds, p plus lambda w is in f, and this inner product can be made arbitrarily small. So that took care of that, number 1. So what about case 2? So case 2, so there are 3 cases we'll be considering. So case 2 just says that wj is less than 0 for some j, meaning j is non-empty. It doesn't care about whether c dot w is strictly less than 0 or equal to 0. By the way, it cannot be bigger than 0, because by assumption w is such that c dot w is less than or equal to 0. That's the choice we have made. Alright, so here we are assuming j is non-empty, which means there is some j such that wj is less than 0. So now what we are going to do is choose a little s, which is the maximum amongst these quantities, pj over minus wj, over this non-empty set, where these indices j run over this non-empty set capital J. And one thing to note is that pj is bigger than 0 for j in j, right? Because first of all, the p is sign constant, right? So pj has to be bigger than or equal to 0 for these sign indices. And if pj were actually equal to 0, then what would happen is, from a claim that we made in the very beginning of the proof, was that whenever pj is 0, no matter what the index j is, then wj is also 0. So since wj is not 0, this is a strict inequality. That means pj is not 0, and since pj is sign constant, that just means pj is strictly bigger than 0. So you have this is strictly bigger than 0, and this quantity is strictly bigger than 0. So this ratio is also strictly bigger than 0. Thus, this little s is strictly bigger than 0. So we can choose an index. So choose an index j star, such that s is equal to pj star minus wj star, and define this new point, or like think of this new point, p plus s times w. So remember, always whenever we are trying to find new point, this w was supposed to be the vector in which we are traveling. So p plus sw will always lie, or will always satisfy the equality constants ax equals p, because aw was equal to 0. But the main question is whether we can find an s such that this is in fact in the feasible set. Alright, and that turns out to be the case, simply because of the way we have defined s. So for all j in this subset of the index set, so for all j in j, we have the jth coordinate of p star. So what was p star? It was p plus s times w. So you are perturbing p in the direction of w by an amount of plus s. Okay, so pj star is nothing but the jth coordinate of p plus s times the jth coordinate of w. Since s is the maximum, look at how we defined it. It's maximum amongst these quantities. So no matter what index j, little j, I choose from capital J, s is going to dominate that, and s is a strictly positive number. So what I have here is, this is bigger than or equal to pj plus pj over minus wj times wj, and all of these are positive numbers. There's no worries about division by 0 or anything of that nature. So this is precisely equal to 0. So what we have concluded is, for all j in j, pj star is equal to 0. Is bigger than or equal to 0. and for all j not in j, of course we have pj is equal to 0. So the sign constants are satisfied. Okay, so for j not in j, we have pj star is bigger than or equal to 0, and for that particular coordinate j star, remember what is j star? J star is that index. So j star is the index where s is equal to pj star over minus wj star. So this capital J is a finite set. So this maximum is attained for some index j that we have named j star. So at that, so the j star coordinate of p star is pj star plus pj star over minus wj star times wj star, and this is nothing but equal to 0. So not only does it satisfy, it's in the feasible set and it satisfies all of those equality constants, all the equality in the sign constant, but it has an additional equality. So at j star, the sign constant has become tight, and I'm claiming that pj star is not 0. Sign constant has become tight. So to summarize, both p and p star satisfy all the constants in S with equality. All the constants in S with equality. So p star was a perturbation of p, and we wanted to perturb it in such a manner such that it had an additional linearly independent sign constant. Now if the constraint xj star bigger than or equal to 0 were dependent on S, then clearly what we would have is pj star star is equal to pj star, right? Because all of these were equality constants, and then you take a linear combination of those. Then pj star star equals pj star. I'm not saying they're both equal to 0, because you do have this sort of constraints, ax equals b. So when you're taking linear combination of these vectors in in, there is an in here, and there is a 0 vector here. So when you're taking linear combinations of this corresponding to the indices in S, so what is going to happen is essentially you're taking combinations of the zeros and elements in B. So I'm just saying pj star p star j star has to be equal to pj star. I'm not saying they're both equal to 0, but this is not the case, right? Why so? Because then that would mean, so if this was equal, if these two were equal, then that would mean this is equal to 0. But pj star we know is strictly bigger than 0. wj star minus wj star is strictly bigger than 0. wj star is strictly less than 0. So this is definitely not a 0 quantity, it's a non-zero quantity. So that would give you a contradiction. So essentially what we have done is shown that both p and p star, these are points which satisfy all the constants in S with equality, but this p star has an additional constraint, which is p star j star equals 0. It is tight at that point, and that is in fact linearly independent. So we can replace S. So S can be sent to S union j star, and p is sent to p star, and then you can repeat this process, then perturb p star accordingly, and so on. So when you added this j star to that index, then correspondingly you have a new f star, right? So this will give you a new f star, which will give you a new w. So this will result in a new w, and so on, and you repeat the cycle. All right. So and as we had made this remark when we were discussing the overall strategy of the proof, that iteratively, if you do this, either you conclude like what we had in essentially we add one new constraint. So let me go back and show you these two assertions. Either we can choose lambda arbitrarily large in such a way such that this p plus lambda w is in the feasible set, and the cost function of these new vectors can be made arbitrarily small, or what you can do is you can perturb P by this amount W, where you have an additional linearly independent sign constant which becomes tight. So that's what we have accomplished even in case 2. Okay, so what's the remaining case? We can figure it out ourselves. So case 1 was, we had said J is empty, and we had certain like requirements of our objective function, or rather C dot W, that is strictly less than 0. In the second, actually we never really mentioned that C dot W is less than 0 or bigger than 0, nothing like that. All we said was J is non-empty. So now the third constant will be two things: J is empty and C dot W is equal to 0. Because J non-empty we have taken care in case 2. So here C dot W equals 0 and J is empty. So that is, for all J, Wj is bigger than or equal to 0. Now we do a similar strategy as to what we did in case 2. So instead of choosing a maximum, what we'll do is choose a minimum. So choose the minimum amongst all these Wj is bigger than 0. Yeah, this could be an empty set. Actually, what I mean by this, choose all those indices such that Wj is strictly bigger than 0, and for those indices look at this quantity Pj over Wj and take the minimum. So how do we know that this set is non-empty? The set of indices is that Wj is 0, because it is non-empty as W is a non-zero vector. That's how we have chosen our W. It satisfies, like we had shown that the nullity of A is non-trivial. It's like bigger than, strictly bigger than 0. There's something in the kernel, and we had chosen a non-zero vector. So we cannot have all of these Wj's, all the coordinates of W being 0. So since we have this assumption, bigger than or equal to 0, there must be some coordinate which is strictly bigger than 0. So we're going to minimize this quantity over all those type of coordinates or all those indices. Okay. Now S is equal to Pj star over Wj star for some J star in J. Sorry, for some in S. Yeah, this is just a finite set. So whatever the minimum is attained at some index. And here Pj star is strictly bigger than 0, clearly, because if Pj star were equal to 0, then by our claim in the very beginning, we would have Wj star is equal to 0. So we have these two things. So S is in fact not equal to 0. So S is in fact strictly bigger than 0. Again, just as in case 2, we have concluded that S is strictly bigger than 0, because if S were 0, nothing interesting will happen. We are not really perturbing P by anything at all. So alright, so as in case 2, so you just have to draw parallels to the strategy. The geometric strategy is P, then you move, and you want to show that you are able to move in a certain direction and stay within the feasible region. Alright, so P plus S, P minus SW, sorry, in this case, P minus S times W. Here it is clear that AP star is nothing but AP minus S times AW. This is 0. So it is AP equals B. So clearly P star is satisfying the equality conditions. And Pj star is equal to Pj minus Wj. And we had that Wj is bigger than or equal to 0. Okay. So this is bigger than or equal to Pj minus Pj over Wj. Yeah, that's because S is always going to be less than or equal to Pj over Wj. S was the minimum of all those things. So minus S is going to be bigger than or equal to minus of that. And so this is 0. So we have Pj star is always going to be bigger than or equal to 0. And for that particular coordinate J star, where S was attaining its like S was actually equal to P j star over W star. So we have P star j star is equal to P j star minus P j star over W j star times W of j star, which is equal to 0. Alright. So P star is feasible and P star j star equals 0, while P j star is strictly bigger than 0. And that's by the same logic as in case 2. Go through these proofs once again and draw the parallels. Because if P star j star is equal to this, I would be claiming that this is in fact equal to 0, which is not the case, because W j star is strictly bigger than 0, P of j star is strictly bigger than 0. That's what we showed here. So in fact that is not the case, and by the same argument we have introduced another, we have found another inequality constant or sign constant which is tight at P star. So this is x j star bigger than or equal to 0 tight at P star, at this vector P star, and they satisfy all the previous constants. So summarizing that, so P star satisfies one more sign constant which is linearly independent. From the constants in S. Alright, and the last thing we have to do is check what the objective function looks like for this new thing. This is C dot P, a fixed number, S times C dot W. What about C dot W? That's 0, right? This is nothing but C dot P. So here what we have done is just moved along the hyperplane. So essentially the direction where we hit the boundary, essentially we just moved along the supporting hyperplane, let's say. So we just moved, let's say we had a face in the tetrahedron, and perhaps the plane that we, the objective function was in fact normal to this face. So if we started here and we moved along this face, the objective function did not change at all. So that is the kind of condition this is capturing. So now we have taken care of all three cases, and we have proved that there is only one of two possibilities. Either what you have is, for all lambda arbitrarily large, C plus lambda W is in F, and you can make the cost function arbitrarily small using these new points, or you have one more equality amongst the sign constant which is linearly independent from what you had previously, and you keep iterating this process, and then you conclude that either the LP is unbounded, or at the end of at most n minus m steps, you reach a vertex. So end of proof. So these are the three cases that we considered, and I keep repeating myself, but I think it doesn't hurt to do that. Is amongst all this computational matrix, matrix theoretic type of thing, you have to always remember is what we are starting with a point P, and we are just looking for a direction to perturb it, and we are hoping that if we start at the interior and we find the right direction, and that direction will determine the offset, how the objective function is behaving, or whether it is increasing or decreasing, and we just move along that direction and hit a surface. Then we have reduced to equality constant in at least one case. From zero equality constants, we reached to one equality constant. Then along that face, we repeat that process. We keep moving until we hit something even one dimension lower, and we keep doing that until we hit an vertex. All right. So as promised, here is the pseudocode. You already saw that this is a very algorithmic process. So how do you tell a computer how to answer question number 3? We had discussed 4 questions. Question 3 was, if F is non-empty, the feasible set is non-empty, how does the computer decide whether the LP is bounded or not? So what you do is you start with P. This is your input P. So first what we'll do, we have to check feasibility. So that anyway you'll have to do, check AB equals B and P bigger than equal to 0. So that anyway you have to check. If not, then P is not really in your feasible set, so the question is wrong. Otherwise, yeah. So using Gaussian elimination, with which matrix? So you look at IN, you have A. So from amongst the INs, you have to choose all those. First of all, choose all those rows where P is tight. So I'm not saying those rows. So here the rows will be linearly independent, of course, because it's just the identity matrix. All the rows are linearly independent. But remember, we will always have to choose A. So if we are choosing the row vectors A, so whatever collection we make, some of them may actually be linearly dependent on vectors in A. So what we will do is first just choose those rows here where P is tight, and amongst them, then using Gaussian elimination, I'll find S, which is actually dependent on P. So I'll stress that here, such that first of all AP is equal to B and Pj equals 0 for j in I, which is SP intersection 1 through n. Yeah, so essentially from amongst those, you just have to find something which is like maximally linearly independent. So that you can do just by using like Gaussian elimination. All right. So now this is not like the full step one. So here you have to make a decision. If number of linearly independent constraints, that are tight at P, so number of linearly independents that are tight P and contain AX equals B is n. In other words, if cardinality of SP is equal to n, terminate. So this is already, we are giving a termination condition. And what should we return? And then return P. P is that vertex. Return P and C dot P. So this is optimal solution, and this is the optimal cost. Okay, so if not, so quite possibly that is not the case. So second step is find non-zero vector, so W in F star. So this F star we defined anyway, like since we are writing pseudocode, we'll explicitly state it out. So xj equals 0 for all j in I, Ax equals 0. Using Gaussian elimination, you just have to solve this equation, right? And of course, this also is a bunch of equations. You pad all those together to find out the mega equation and solve it using Gaussian elimination, and ensure that C dot W is less than or equal to 0. And you can do that because you just find a solution, just compute C dot W. If it is strictly bigger than 0, just take the negative of W. So that also you know how to do it with a computer, at least like theoretically. So now the third thing is, mostly essentially you'll just run through all these indices j, find j which is defined as all those indices where wj bigger than 0. So this is going to be routine. So you just go through the array of this vector w, and then you look at each individual element and just return all those labels or indices where it is strictly bigger than 0. So that also you can do. Once you have done that, so now we have these conditional statements. If C dot W is strictly less than 0 and j is empty, what do you do? Conclude that LPS instance is unbounded. 5. Elif or else if in Python, like the thing you'd be using is called elif. So else if j is not equal to the empty set, then what you do is choose S equals max of all these indices, Pj minus Wj, replace P with P plus SW and I. So by the way, here let's define J star to be the smallest, to be the index corresponding to this maximum value, so argmax. So that is the notation, it's the maximum argument. So this is a function of J. If you think in terms of that, it's a function of J. You're trying to find the maximum value of this function. Argmax just tells you like at which point is this function's maximum attained. So that's all I'm saying. So it's argmax of Pj minus Wj. So here you have to do two things. So if J is not equal to empty set, replace P with P plus SW. So this computation again is like a sorting algorithm, you can say. You're trying to find a maximum of an array of numbers. So that is something which is standard. So now you replace P with P plus SW and I. This is an indexing set, which is consisting of all those sign constants. So SP was nothing but I union the ones corresponding to A, so n plus 1 all the way to n plus n. So that's the I we are talking about. Again, I was dependent on P, so I should probably write IP. So J in IP. So replace and IP with IP union J star. Now we don't have to prove that like things in IP union J star correspond to linearly independent constant, because it was part of the proof. Here we're just talking about pseudocode. Like if we run this algorithm, the computer will tell you all the answers that we are trying to find now. So the proof is already done. All right, the last step 6 is else. So the final remaining thing is else, that is C dot W is equal to 0, J equals empty. So I mean that's the only remaining thing, so I don't really have to say else if or whatever, just else. Here we replace P with P minus S times W and IP with, again it's similar to what we did in number 5, IP union J star, where S is equal to minimum of all those indices J such that Wj is bigger than 0, so Pj Wj, and J star is equal to argmin of J such that Wj is bigger than 0 of Pj over W. Alright, so anyway, so determining this set is also easy enough. You just scan through the whole array, you figure out all those indices J, and then compute this array of numbers Pj over Wj, maximize, minimize using your favorite say sorting algorithm or what have you. Alright, so now after you have done this, go to step 1, because now so when does step 1 terminate? Oh, by the way, here I should say conclude that LPS instance is unbounded and terminate. So this is another way to terminate this program. So here note that we are actually updating two things. We are not just updating P, we are also updating IP, the set of linearly independent things where the sign constants are tight at that particular point P. So of course you can only increase this set finitely many times. The upper cap is the size of this set cannot be more than n. So this will terminate. Either it will terminate at step 1, where the size of where the size of SP is equal to n, or size of IP equivalently is equal to n minus m. So this is where this will terminate. If it doesn't terminate there, it will terminate at number 4. So this is the pseudocode to keep in mind. The computer can tell you whether like your LPS instance is bounded or not, because if this returns it, if it stops at 0.4, it will output saying that this LPS instance is unbounded. That is what it will output. If not, what it will end is it will tell you, it will return. Yeah, so remember here return P and C dot P. So perhaps in step 4 I should say terminate, return meaning print LPS is unbounded. Okay. So using this algorithm, you are able to either figure out the an instance of a vertex which has lower value than p, or you know that it is unbounded. So next class, what we will do is in fact turn to the fourth question, which is, now that we know that when the LPS is unbounded, and if it is not unbounded, we know how to find a vertex. So next class we'll try to figure out a method of traversing the vertices in an efficient manner, so that we find the best vertex amongst the finite lineae that are available to us. So see you next time. Bye bye.